right, let's look at some practice problems. Yay. Okay, in this first example, I have this discrete time system. I go ahead and form the control map up to time n, which in this case is 3, and which also happens to be giving us the controllability matrix. So here's B, here's A times B, there's A squared times B. Okay, because of the fact that I have multiple inputs, I have 2 columns in my B matrix, my controllability matrix is not square. Okay, it's fat. So this is my controllability matrix. I can go through and compute the controllability Gramian up to time n, which is QC transpose, and I can show it's this. And I can show that the eigenvalues of this are all strictly positive. Therefore, my system is this is my controllability Gramian being positive up to time n means my system is controllable. Okay, so my system is controllable. I can put my system in modal coordinates. So here's my eigenvector matrix. If I use this eigenvector matrix and put my system into modal coordinates, notice I have a diagonal matrix here, and I have this. Now, because of the fact that I have no rows of 0, therefore my system is controllable. So it turns out that the modal properties say that if I have any row of 0, that corresponds to an uncontrollable system. But in this case, I have no rows of 0. If I look at the PHR test, so the PHR test, so here, if I take the characteristic polynomial, here's my characteristic polynomial, I factored it, so my eigenvalues are -1, -2, and -3. If I plug in into x of c, these eigenvalues, these are the matrices I get, and I can go through and show that each of these have rank equal 3. That means my system is controllable. Because my system is controllable, I can actually apply a state feedback so that I can have arbitrary eigenvalues. So I want to use a state feedback, but if you recall, the formula that was used, the Ackermann's formula, required that the system be single input. So in this case, I can fake a single input if I introduce a matrix U1, where U1 is chosen such that A and B times U1, so now this is going to be a single column, if A and B times U1 is controllable. So I can choose, for example, this matrix. Okay, so I can show that if I use this U1 matrix, that A times B U1 is controllable. And so as such, we have a new controllability matrix. Okay, and so here's my new B U1, A B U1, A squared B U1. So this is my new controllability matrix. This is what I get. So notice that by introducing the U1 to B, I now get a controllability matrix that is square. Okay, and we can go through and show that in fact this is non-singular. So this is my controllability matrix. I now want to choose my alpha C. That is, I want to. This is a discrete time system, and so remember, a discrete time system is stable if all of the eigenvalues are inside the unit circle. So I'm going to put them not only inside the unit circle but at the origin. Okay, so that's like, you know, as stable as they can be. So this is the characteristic polynomial for a matrix that has all its eigenvalues at the origin. Okay, and so if I plug in alpha C of A, if I plug in A here, I'm going to get A cubed, so this is A cubed. So that's alpha C of A. And so Ackermann's formula basically says this. So notice I have the Q bar here because I'm using the different, instead of B, I'm using BU1. But notice it requires the inverse because the system must be controllable in that case. So here's the formula, alpha C of A, that's A cubed. And so I just multiply this out, I get this expression. So this is my F1. And so F, which is the actual state feedback gain, is given by U1 F1. And it's given by this. Okay, and so I can now apply that. So I can apply A plus B times that F, and this is the matrix I get. and I can show that this has characteristic polynomial equal to z cubed. So this matrix actually has all of its eigenvalues at the origin. It's kind of hard to tell by looking at it that that's the case, but indeed it is the case. So notice if I took this column, multiplied by -4, I would get this column. Okay. Whoop. So anyway, I can see that it's definitely non-singular. So what would happen then is actually this matrix is actually if you would get a Jordan form from this, and all the eigenvalues are 0. Okay, so but that's the characteristic polynomial. So we'll see later how this can be used in actual control, but that's the basic idea. So it turns out that you can actually, for the tests that were given, it's actually easier to see how the tests work when your system is not controllable. It's easier to see than when it is controllable. So now I'm going to start with an uncontrollable system. Now, I already know it's uncontrollable because I've picked it that way. So notice that all of these system examples that I use often are all have integers. Okay, that just makes the whole calculation a little easier to look at. It doesn't change the fact. It's not required. I could have, irrational numbers or whatever as elements of this, but I'm choosing integers just to make the calculation simple. Okay, so the controllability control map up to time n is equal to QC, which is given by this expression. Here's my QC, and I could go through and show that this system has controllability Gramian given by this, and I can show that in fact this has 0 determinant. So the system is not controllable, which you already knew because I told you it was, but now you know for sure because we've actually done some calculations with it. Here is my eigenvector matrix. When I apply it to the system, this is the matrix I get. So notice here I have these 3 eigenvalues, and here's my B matrix. So notice here I have a row of zeros. Okay, that row of zeros is associated with this eigenvalue. Now remember, for a discrete time system, the eigenvalues need to be inside the unit circle. In this case, all of the eigenvalues are either on the unit circle or outside the unit circle. So in particular, I have one eigenvalue that is outside the unit circle, and it's not controllable. So this system is not stabilizable. Okay, I mentioned the definition of stabilizable. The definition was that all of the unstable eigenvalues are controllable. In this case, I have an unstable eigenvalue that is not controllable. So this system is not stabilizable, which it's just a contrived example anyway, but that would be a bummer because that means your system is blowing up and there's nothing you can do about it. So that's not a good thing. But anyway, so I can see in modal coordinates, I can see that uncontrollability by seeing that row of zeros in the B matrix. Okay, so by putting it into modal coordinates, I can actually see the uncontrollable mode. Okay, so remember the modal aspect of controllability involved left eigenvectors. Okay, so here's my eigenvector, but in order to go to diagonal to this form, I actually multiply on the left by V inverse. Okay, and it turns out that the inverse of the eigenvector matrix gives you the left eigenvectors. Okay, so one way of obtaining left eigenvectors is to take the inverse of the regular right eigenvector matrix. Okay, so that's actually kind of an interesting thing. So I would actually be multiplying by V inverse times B to get this matrix. Okay, and so that's actually multiplying by the left eigenvectors of a matrix. I now use the hottest test. So here's the characteristic polynomial. And so I plug in the characteristic polynomial into XC. And so these are the various matrices I get. I can check this and find that the rank of that is 3. I can find that the rank of this is 2, and the rank of this is 3. So I can see, using the PHR test, that I have an uncontrollable mode here. In terms of state feedback, in this case, there is no U1 that can be chosen so that this A, B times U1 is controllable. If AB is not controllable, then adding this matrix here is not going to make it any more controllable. Okay, so no matter what we choose for f, our characteristic polynomial, that should say a plus bf, is going to be of this form. Okay, it's going to be of this form. So our transformation, so here is a block triangularizing transformation that I have come up with. I've picked it. Okay, so when I apply this transformation to the system, this is the new system that I get, and I can see it's block triangularizing. Okay, I get a block of zeros here. This part is square, this part is square, so that's a block triangularizing transformation. And I can see in the process I got a row of zeros coming out. So now this matrix is not a matrix of left eigenvectors or eigenvectors, but obviously there's some relationship behind them. So, but anyway, I get this situation, a block triangularizing transformation that gives me a row of zeros. Since I have a block triangularizing transformation that gives me a row of zeros down here, I know my system is not controllable. And in fact, there's the uncontrollable mode. Boom, pops out again. Now, the thing about block triangularizing transformation is that in general, there's an infinite number of block triangularizing transformations. So here is another block triangularizing transformation. So see, I get a block coming out here. But notice that when I use this transformation, I get something that's not zero here. Okay, so, and that's because this mode is actually, this is a mode of the system, and it is a controllable mode. Okay, so what this shows is that even though I have a block triangularizing transformation, just that by itself only is really only concerned with the A matrix. Okay, and so you actually, there are, to find a block triangularizing transformation that would give a row of zeros actually requires a little bit more effort. Okay, you actually have to look at the controllable subspace and the uncontrollable subspace and so forth, and get a transformation based on that. Okay, so not every block triangularizing transformation is going to give you a row of zeros for an uncontrollable system, as this. And the reason is that the uncontrollable mode is actually in here, not in here. Okay, so we talked about reachable set. So for some systems, I can apply an input to a system, and this is the result in the state space, in the phase plane, and I can see that the response of the system just moves along this line. Here's a system. It has this controllability Gramian, which I can get singular value decomposition here. Okay. And now I'm going to define z related to x this way. So x and z are related this way. Okay, so this was what I was talking about earlier. Now the reason I do this is because I want I want to be able to specify z. Z here specifies a circle. For any value of theta, this lies on the circle. Okay, and so if I define x to be based on z this way, then I can see the reachable set, which is this quantity, and I can see that in fact I get an ellipse. Okay, so this expression involving the controllability Gramian gives me a circle, and so the reachable set is an ellipse. Here I have two matrices. Which of these is cyclic? Well, the definition of cyclic says there is some vector such that I can form a controllability matrix using that vector that is non-singular. Okay, so I can do this symbolically, or it turns out there's actually a little principle behind whether a matrix is cyclic or not. So I have these two matrices. If I find their Jordan decomposition, so A1 has this Jordan decomposition, A2 has this Jordan decomposition. So here are the eigenvector, generalized eigenvector matrices, and here are the Jordan forms for the two. So notice that both of these matrices have all the same eigenvalues. They're all the eigenvalues are at -1 for both of these two matrices, A1 and A2. This one is a standard Jordan form, and that is a single Jordan block. I have a single Jordan block. Okay. This one has two Jordan blocks, a 2x2 Jordan block and a 1x1 Jordan block. So it turns out that for a system to be cyclic, it can only have one Jordan block for each eigenvalue. In this case, I have two Jordan blocks for this eigenvalue -1. So this one is not cyclic, this one is cyclic. So one way to check whether a matrix is cyclic or not is by checking the Jordan form of that matrix. If the Jordan form has one Jordan block for each eigenvalue, then it is cyclic. If not, then it is not cyclic. So I can go through and show that there is no x1, so that if I use this matrix, I will get a Jordan form that is I won't get a controllability matrix for any x that will be non-singular. Okay, here we have a system. We want to see the reachable set where U is an L infinity, that is bounded magnitude. Magnitude bounded by 1. Okay, so I want to check out this reachable set. In this case, the system is controllable, and so we can try a number of bounded signals and trace their paths, and we can also try some bounded energy signals. Okay, so remember, a bounded energy signal is not necessarily bounded magnitude signal. Okay, so we know that for bounded energy signals, we have this is my Gramian, and this Gramian defines an ellipse. And so in the state space, my system should meander around in that space. So the black is that ellipse. Okay, the black, and I've applied a number of inputs to the system. And so here are the different inputs to the system. There's a step input, bounded magnitude. Okay, so remember, because it's bounded magnitude, of bounded magnitude, does not mean it's bounded energy, right? And so the finite energy ellipse says that if I have a signal of energy less than 1, it will stay within this ellipse. Okay, and so I can see that the step function is not finite energy, and so I can actually leave the ellipse. A rectified sine wave also is not finite energy. It leaves the ellipse. Okay, a chirp signal also is not finite energy, but I can see it's kind of hard to see, but I can see that it actually still stays within that ellipse. A random signal stays within that ellipse. A sawtooth signal comes really close to the boundary, but stays within that ellipse, and so forth. So I can look at a number of signals, and so the finite energy ellipse actually gives kind of a good bound, but it's not perfect, because there are some signals that I can apply that can exceed that bound, can go outside the boundary. Here's a system, and this is in continuous time. I want to find an f such that a plus bf has this characteristic polynomial. So in this case, QC is given by this. I can see that its determinant is not 0, so a system is non-singular. I can use Ackermann's formula, and I can show that a plus bf is given by this. And so in this case, I can actually even see the eigenvalues, and the system is, in fact, has those eigenvalues. So I wanted those eigenvalues, that characteristic polynomial, and I indeed have that characteristic polynomial. So a number of properties of systems. We're getting into some more complicated examples, but this issue of controllability is of fundamental importance in examining the properties of systems.